So this is the beginning of chapter 18, which starts a series of 3 chapters, 18, 19, and 20, that are all connected to each other, and they're all related to light. So chapter 18, they titled Let There Be Light. So this is the background stuff. There's really not much in chapter 18 that would be new to you. From things learned from Gen Chem and then experiments potentially done in Gen Chem, but either way, we're still going through it. So when we're looking at light, light is a wave. It's also a particle, but we're not super, well, we'll get there. But as a wave, with light, we're looking at its wavelength, which is the literal length of a wave. So if you pick one spot in the wave and go to its neighboring wave and measure the distance between them. So wavelength will be in the unit meters, but often the metric prefixes are used. We see things like micrometers, nanometers, picometers when we're looking at wavelengths. So we see the metric prefixes with that. The other property that we care about when we're looking at waves is not actually amplitude. It's a property, it's important, but we're not going to worry about it, is frequency. Which has the Greek symbol nu. I guess I should explain. That's the Greek symbol lambda. That's the symbol that stands for wavelength. Okay, so frequency is waves per second. So it's counting how many waves per second. But we don't use the word waves when we're doing this. So we use the unit just per second. So seconds -1, or you could write 1 over seconds. We see metric prefixes show up with this as well. And the most common symbol that you hear about frequency is actually hertz, which is just the same thing as inverse seconds, as 1 over seconds. It's like it got its own name. A joule is another example of a unit that they gave a name, but a name to, instead of writing the symbols, because a joule is a kilogram meter squared per second squared. But instead of writing that, we just write capital J for joules. So instead of writing inverse seconds, seconds -1, they write Hz, which stands for hertz. So when we're using frequency, again, we're going to see metric prefixes show up with that. When we use wavelength, we're going to see metric prefixes show up with that. But when we go to our calculations, which is what is upcoming, we always want to remove the metric prefixes when we're comparing wavelength and frequency. Okay, so, and there's my frequency. I just got real excited. So like looking at these two pictures, the top one has a higher frequency, more waves per second. If we say from here to here was 1 second, I see many more waves that went up and down and up and down. The bottom one has a lower frequency. Fewer waves happened with that. Okay. So inverse seconds are hertz with that one. And when we're talking about light, there is a constant speed of light. Yes, there's a lot of work being done with that right now for scientists, certain scientists looking into that. But we're going with light has a constant speed, the speed of light. So all waves of light go the same velocity. 2.998 times 10 to the 8th meters per second is its speed, its velocity. So this wavelength and frequency are very much related to that, and we're going to see that in a second. But the way that this works is if all waves of light have to go the same speed, but some of them have longer wavelengths. So like the bottom one has a longer wavelength. That's a longer distance than that. So that's like a longer wavelength, longer lambda, and it's a lower frequency. And this one has a shorter lambda, but a higher frequency. That's what we see, is the wavelength and the frequency balance each other out. So the way I think about this, something with a short wavelength is like a short person who has very short legs, and a wave with a long wavelength is like a really tall person who has very long legs. But if they're both light, so they're going the same speed, then the short person and the tall person are walking down the hallway together next to each other, going the same speed. And when that happens, the short person is taking lots of short steps. Like their steps are very close together. Their feet are close together when they take their steps, but they have to take, maybe 5 steps. And then the tall person, their steps are very long. Their legs are very long, so they're really long steps, but they take fewer steps. So maybe they take 2 steps the time it takes a short person to take 5 steps. So there it balances out. The shorter the wavelength, the shorter the length of the step, the more steps you have to take, so the higher the frequency. The longer the wavelength, the longer your legs, the bigger the step, the fewer steps you have to take, so the lower the frequency. That's what we see happening with light. So light is the electromagnetic spectrum is looking at the entire range of light. Um, so, oops, oops. Didn't mean for that to happen. Sorry. We normally focus on the visible spectrum of light, which is what we see with our eyeballs, but it goes all the way from gamma rays to radio waves. We deal with most of these all the time. It's just we don't normally think of them as light. We think of like what we see with our eyeballs when you switch the electrical switch and the light bulb shows on as light. So the differences between these types of light are their wavelengths and their frequencies. And in this, you can see up at the top, up here, it shows the order for increasing wavelength. So radio waves have the longest length of a light wave, and gamma rays have the shortest length in terms of light. And when we're looking at the visible spectrum, what we see with our eyeballs, they're increasing in wavelength. The blue purple has the shortest wavelength of what our eyeballs pick up, and the red has the longest wavelength for what our eyeballs pick up. So what I want you to know from this is know the order. Gamma, X-rays, UV, ultraviolet, visible, IR, infrared, microwaves, and radio waves. Know that's the order from shortest to longest, or the longest to shortest. Either way, know the order. And know the visible range spectrum, that purple is the shortest wavelengths and red is the longest wavelengths. And I would recommend you having a pretty good idea that the visible range is from 400 to about 750 nanometers. That's going to be important as we get to later chapters. So that from that image, that's what I would know. Don't worry about memorizing the numbers like here. Like I wouldn't say, so here's a random wavelength. What range is it in? No. I'm not going to do that. But I want you to be able to identify that X-rays have a shorter wavelength than microwaves. Like I want you to know that because that's common knowledge for scientists to be able to discuss electromagnetic radiation and knowing the order of them. Again, don't know the numbers, know the order. The only numbers I want you to know are for the visible spectrum, so you would recognize if something is in the visible range or not, because again, a pretty common thing that scientists have to be able to do. So the speed of light is always abbreviated by the lowercase letter c, and its value is 2.998 times 10 to the 8th meters per second. That is a constant, meaning I will always give it to you. And then the mathematical relationship between the speed of light, the wavelength, and the frequency is right here. Remember, c stands for the speed of light, so we would just substitute that number right there every time we use this equation. That is wavelength, and this is frequency. And if we look at the units on the speed of light, its units are meters per second. So the wavelength must be in meters, and the frequency must be in per second. So it can't be in nanometers or micrometers, and frequency cannot be in megahertz. Remember, hertz is the same thing as a per second. So you have to get rid of all your metric prefixes before you use this equation. I'm not going to do an example of this because I truly do trust your ability to, if you're given, the constant's always the same, and if I told you the wavelength and asked you to solve for the frequency, or I told you the frequency and asked you to solve for the wavelength, I trust in your skills to divide numbers, I guess. So when we're talking about light, some more background, we already, I think, reinforced that light is a wave. But light also comes in chunks or pieces or packets that are called, that Max Planck is the scientist that first studied this and discovered this. He called them quanta. We typically call them photons. So a piece of light is a photon. Okay, and we can calculate the energy of one photon using Planck's equation, which is right here. H is a constant. E stands for energy, which will be in joules. And the thing that looks like a V is actually the frequency. That's the nu from the previous slide. And you're going to see this set of symbols, h nu. if you see that just floating around somewhere, not like it's being calculated, it's just somewhere, that's representing a photon, so a piece of light. So it's talking about light. The way that light works, since it's a wave and a particle, it always we have known amounts of energy that the light can have. It moves in a wave, but it's made of pieces. So the wave, this is not going as well as I want it to there. It's chunks that form a wave. So it's like if we all joined hands and did the like snake thing where the person in front, kind of directs where you go, and you make a kind of a wave pattern. We would all be individual human beings. We just happen to be following each other in a line, and that line happens to be making a wave. So that's how energy works. So this equation calculates how much energy does one piece of light have at a specific frequency. Now, using substitution, this equation is the same as this equation. That equation, all I did was substitute it in. I solved this equation for frequency and then substituted that in. So instead of h times frequency, it's h times c divided by lambda, which is wavelength. So you can use either version of this. H is a constant, so it'd always be given to you as well. So light is a wave, light is a particle, and we can calculate the energy of that particle. So this is the new part of this little section. Everything in here should hopefully be review. Most of the slides I've shown you so far, I took from my Gen Chem 1 PowerPoint slides. But this is a new one. It's called wave number, and its symbol looks like nu, like the frequency symbol, with the little tilde, the squiggly line above him. And its units are inverse length. So inverse meters, even though most of the time when you see this, you're going to see this in organic chemistry when you're looking at infrared spectrum. It's usually inverse centimeters. So what it is, we're just taking the wavelength, like the inverse wavelength. 1 divided by wavelength equals wave number. Okay, so that's the name of this symbol. That symbol is wave number, and its units are inverse meters or inverse centimeters. So just again, we've got Planck's equation from the last slide, h nu, which is the same thing as hc over lambda, which is the same thing as hc times wave number. These are all versions of the Planck equation. All three of them calculate how much energy there is in one photon of light. So wave number is the new one. Wavelength and frequency, hopefully you've heard of before. Knowing that light is a wave and a particle, hopefully that's not new as well.